What's up, guys? Welcome to part 3 today. We're going to be investigating or discussing bonding of covalent, ionic, and metallic compounds. We're going to be talking about how to name them, and we're going to be talking about some rules for naming. So let's just jump right into it. In reality, there's a few different types of compounds or types of ways that matter exists. The first one is just a pure element. And this is just pure elements from the periodic table that are existing, like pure hydrogen just exists. It's a diatomic molecule, but it's only bonded to hydrogen and there's nothing else there. There's also a category of matter called mixtures. And there's two different categories of mixtures. There's homogeneous mixtures and heterogeneous mixtures. Homogeneous mixtures have different elements mixed in or different compounds, but the different compounds or different elements are not distinguishable when you look at the compound. The mixture is going to look like one thing, even though there are other things mixed in. However, a heterogeneous mixture of elements or compounds is going to have distinguishable differences within the mixture. So something like a smoothie would be a heterogeneous mixture because you can see little bits in the smoothie. You can see little bits of, like spinach leaves or little fruit bits. So that would be a heterogeneous, meaning different, heterogeneous mixture. Then you've got something called a compound. And a compound is elements that are combined at a chemical level. So they're sharing electrons. They are chemically combined. Just in a mixture, they're not chemically combined, they're physically combined. But in a compound, the elements are chemically combined. And then there's a term that we want to use when we're looking at bonding that's going to be huge, so important, and that's the term electronegativity. And this is the affinity that one element's electrons have for another element's electrons. How much do they want to grab those one element? How much does one element want to grab the electrons of another element? That's what electronegativity is. And that's going to determine the activity or the reactivity of a lot of these elements. Now we just talked about some different categories of matter. Now we're going to talk about some subcategories of compounds, right? The things that are chemically combined. And so we have 3 categories. There's covalent, ionic, and metallic. And we're going to write down some distinctions, right? And so first, we can diagram these bond types differently. So if I was to draw an electron dot diagram for something like fluorine gas, we have fluorine, 2 fluorines, and they each, if you look at the periodic table, have 9 total electrons, and they're in column 17, so they're going to have 7 valence electrons. So if we draw the energy levels for these guys, the first energy level has 2 valence electrons, and the second energy level is going to have 7. So we'll have 1, 2, 3, 4, 5, 6, and then the 7th one, 1, 2, 3, 4, 5, 6, and the 7th one. But in covalent bonds, okay, the electrons are treated, they're shared equally because the electronegativity, which is how much this atom wants to take electrons from that atom and how much that atom wants to take electrons from that atom, those values are so similar. So what's happening is these 2 outer electrons are going to be shared equally between the 2 atoms. And so this is how we would diagram a covalent bond if we were doing electron dot diagrams. But ionic bonds are going to be different. So let me show you an example of that. So we've got sodium, and sodium has 11 total electrons. But I'm only going to draw its outer energy level, and it's only got 1. It's in column 1, so it only has 1 outer energy level. And then let's say it's bonding to chlorine. And chlorine, if you look at the periodic table, has 17 total electrons, but 7 valence electrons. And I'm just going to worry about the outer energy level because those are the only electrons that are doing anything. This guy has 1, 2, 3, 4, 5, 6, 7. Okay. And if you look at the electronegativity of these 2 atoms, sodium sodium has a really low electronegativity. It doesn't want to steal electrons very much, but chlorine has extremely high electronegativity. So it's ready to snag some electrons from somebody. So what happens is these guys, they're not going to share electrons. Sodium is actually going to give up its outer electron, and chlorine is going to steal that one, so that chlorine has a full outer shell, and actually sodium goes back to a lower energy level, and it also satisfies that octet rule. So this is how we would diagram a ionic compound. And then for metallic bonds, these are a little bit funky. What's going to happen here is we're just going to draw a bunch of nuclei, and then the electrons are really, they're just flowing around, they're free flowing through the whole material, through the whole metal alloy or pure metal. They're not really associated with one specific nucleus, they're just able to free flow around. So how are these guys treated? The covalent electrons are being shared, and that's based on the electronegativity. Ionic compounds are stealing electrons, or the more scientific word would be transferring, where an electron is transferred from one to the other. And then finally, for metallic, we're just going to use this term free flowing. Okay. Now, there's types of elements and the electronegativity scale that are involved with each of these is very important to remember. For covalent compounds, these are going to happen between two nonmetals. And they're going to have an electronegativity difference of between 0 and 0.4. Okay? And so we'll be able to look up the electronegativity values online whenever you feel like you want to. But for ionic compounds, these types of bonds are only going to happen between a metal and a nonmetal. And they're going to have an electronegativity difference between 0.4 and 1.7. Okay? And then metal bonds are going to happen between metals, just only metals. And we're not going to worry about the electronegativity because the electrons aren't being shared or transferred, they're just flowing around. And so there's some common properties that you're going to see across covalent compounds. They're more malleable, they're more flexible, they don't really conduct heat, they don't conduct electricity very well. Ionic compounds are more brittle, they conduct electricity when they're dissolved in water. And then metallic compounds, they're ductile, they're malleable, they conduct electricity really well. Those are just some of the common properties. All right, we're going to look at naming covalent, ionic, and metallic compounds. First, if you have a compound such as CH4, we're going to write out the name of the first element, carbon, and because there's only one, and it's the first element in the formula, we're not going to put any prefixes, but normally, if there is a subscript, you're going to put a prefix so that you know how many there are for covalent compounds. But because it's the first one and there's only one, we don't use mono, so I'm just going to say carbon. Then I look at the subscript for the second one. 4 is tetra, so I'm going to say carbon tetra. And then we take the name of this element, we chop the end of it off. So it was hydrogen, now it's hydr. And we took the gen off and we put the letters IDE. So tetrahydride. And we call this element, or this compound, carbon tetrahydride. Here's a list of some of the prefixes. They go on for a while, but we're only going to use monoditride, tetrapentahexa for the most part. Okay. When we name an ionic compound, you're going to take the metal, which is on the left. You're always going to put the metal on the left, which is the cation. And you're going to write the cation's name first. So we'll just write out magnesium. And then we'll take the anion, which is the negatively charged ion, because This is the one that takes the electron. The cation is the metal that gives up the electron. And we're going to write that name. We're not going to use a subscript. Okay, so we're just going to write chlorine, but take the end off and write chloride. Okay, so magnesium chloride. If instead of this metal being in column 1 or 2, you have a transition metal, you're going to have to use Roman numerals. And you're going to put the Roman numeral after the metal's name. So, for example, let's do something like silver chloride. Okay, for silver, you're going to do something like silver, and you'll do Roman numerals. And because chlorine has a -1 charge each time, each chlorine is going to take 1 electron. So this is going to have a negative charge, and there's 2 of them, so it's 2 negative charges. The silver is going to have to give up 2 electrons. And so we would put 2 there, and then write silver. So this tells you the positive charge on the silver. Okay, that's what the Roman numeral is telling you.